My name is Ahmed Hussein Salama. Today I'm gonna present our paper, which is called Modeling and Energy Analysis of Adversarial Perturbations in Deep Image Classification Security. Our today outline, we're gonna through introduction and then background, and then we're gonna explain how we have collected the data sampled in our analysis, and then we're gonna show how we have modeled the adversarial perturbations in the DCD domain, and then we're gonna do an extra analysis for the perturbation energy and compare and split it in two parts, which is a background and object using one of the well-known CAM algorithms, and then we're gonna analyze the perturbation energy concentration in the DCD domain. In I'm gonna start by mentioning different type of adversarial attacks. Adversarial rotation attack. It's just an attack that you can rotate an image and you get uncorrected label, and adversarial patch attack, which you can add a batch of image to the input image, and you're gonna get uncorrect attack, which is here persons, but the predicted output is no persons. And the last type of attacks is adversarial perturbation attack, which is the main focus of our today work, where we given a well-trained DNN and an input image, we can add an imperceptual perturbations sigma that can be easily crafted and added to the input image to generate an adversarial example x node x prime, and the output of the DNN. In our paper we're gonna answer main two questions. The first question will be, can adversarial perturbations could be modeled through different attacks? For example, as you see here on the right, we have the original image and different perturbations added to this original image. So as you can see, these perturbations are in the spatial domain, and it is intuitively we can say that they cannot be modeled. So could they be modeled in another domain than the spatial domain? And also, could we is the energy the perturbation energy of this image is same as the perturbation energy of this image? Because as you see here, the CW attack will be have less energy than the other kind of attacks. So in our paper we're gonna answer these main questions. So let's start with what is adversarial perturbations. So what as adversarial perturbation is just we craft a certain epsilon that can be added to x, where it gonna be still in the range of 0 1 after normalization, where this crafted perturbations gonna change the predicted label of the original image. This crafted input is gonna be imperceptual in the human eyes with a certain budget, and we can design craft this epsilon given a target label T. And also in our background we're gonna use class activation maps, which is called eigencam. Eigencam is based on a singular value decomposition and can be applied to any DNN based computer vision model. It is also robust against adversarial examples in terms of segmentation. In this figure, we show that the eigencam is applied to the original image and its adversarial, and the adversarial example crafted by the BGT, and the underlying DNN used here was ResNet 18. As you see in the segmentation in terms of background and object is also identical in both cases, and the object is located correctly in the adversarial example as well. And for our model, we're gonna use a TCM model for modeling the distribution, where it is one of the popular distributions proposed by Professor Young to model heavy tail distributions, where B here gonna be have a range from 0 to 1, and YC gonna have the range of 0 to A, where A is the largest magnitude that the Y can take, and YC it is the split point between the uniform distribution and the main body of the distribution. For Fy theta, it is a probability density function with parameter theta, and we assume that it will be symmetric around its origin. And A and YC are assumed to be known, otherwise the rest of the parameters will be estimated using the maximum likelihood. For testing, we have used chi-square goodness of fit test to verify whether the data samples xi follow a certain probability distribution with the parameter of theta. To compute the chi-square test, the data samples are first grouped in B bands, and the chi-square can form as follow, where NBI is the observed counts in the data samples and EJ is the expected counts on the hypothesized distribution. Data collection. For collecting our samples, we have used the BGD and FGSM and CWTX to attack ResNet 18 and ResNet 101 with the same perturbation budget for the validation set of ImageNet. To further compare between each attack, we have used cross entropy as a loss function, and we set the target to be 40. We have randomly selected 2000 successful images with the following properties. With the following properties. Each image has a minimum of 500 blocks with an 8 by 8 size for both the objects and the background to have a fair comparisons between the number of samples in each set. And a randomly corrected classified image from the validation set is damned successfully, and a target adversarial perturbations for the selected original image can be crafted by each of the BGD and FGSM and CWTX. And this table is the following is the settings that have been used in our experiment. We have applied the EigenCam to each selected original image to segment it into its object and background blocks. Then a 8 by 8 block is deemed an object if the sum of the blocks is greater than or equal 63, and otherwise it's gonna be considered as a background block. For each targeted adversarial perturbations, we have converted the RGB space to YCPCR, and then we change it to 8 by 8 blocks, and then we have done a 2D DCT, and then we flattened into one dimension in the zigzag order this section we're gonna model the adversarial perturbations in the DC domain. The intuitive thinking that the adversarial perturbations are purely random. However, it turns out that it's not true. This figure shows a histogram of the DCT coefficient of all DCT blocks of the adversarial perturbations crafted by the CW attack for the random selected 2000 images. This figure shows the BDF of the GGD and GGG TCM and TCM based on the Laplacian distribution and the Laplacian distribution itself. From this figure, it is quietly clear that the GGTCM is fits the DC coefficients of the adversarial perturbation crafted by CW. And to further support our observation, we calculated the KL divergence between the histogram and each fitted model, Whereas the smaller the KL divergence, the more the better the fitness, the better the model will fit. So from our previous empirical results, it motivated us to further investigate the model of the adversarial perturbation in the DC2 domain by using the goodness of fat. So we have two main hypotheses. The first hypothesis that it tests the model and the histogram, and the alternative one where they are coming from the same distribution or they came from different one. We have applied a square goodness of fat test with significant level of 0.05, and we quantize the coefficients into 15 band. We have tested the above hypothesis for random choosing images from 2000 images, and the test shows a respective p-value for each frequency, where the null hypothesis would be rejected if the p-value is smaller than 0.5, otherwise it will be accepted. As we show here in this figure, this is a 64 coefficients and this is a significant level. So for the BGT attack, 62 were accepted, and CW attack 64, and FGSM is 61, which indicates our model, GGTSM in the DC2 domain can model our perturbation, our adversarial perturbations. We now use a statistical method to compare the adversarial perturbation energy in the background and with that in the object. As mentioned before, we segment the object relative to the background using EigenCam as a segmentation method. So how we calculate our perturbation energy, we square all coefficients and sum over the 8x8 block, and then we average for the whole block for one image. So we first test whether or not the adversarial perturbation DCT block energy in the background that in the object follows the same distribution used by setting up the homogeneity test. So we have two hypotheses, so the null hypothesis and the alternative one. So the null one if both of them, the object and the background, came from the same distribution, and the null if they came from different distribution. So for the homogeneity test, the chi-square homogeneity test, the significant level, we set it to 0.05, and we quantize average DCT blocks into 67 pence. It turns out that FGSM attack above the above null hypothesis is accepted by a p-value of 0.76, but for the BGTI and CW attack, the null hypothesis was rejected with a value of close to 0. To compare the average adversarial perturbation DCT block energy in the object and the background, we next estimated their respective mean and confidence interval based on the data samples. To estimate their confidence interval, we apply technique of empirical bootstrapping and set the confidence interval to 0.95, and we have resampled the data 5,000 times for both ResNet 18 and for the data sampled from ResNet 18 and ResNet 101. As we can see here, the resulting estimated mean and confidence intervals, it's clear that the CW attack for both models has a significant adversarial perturbation energy in the background and then the object. So as we can see here, this is gonna be our background, and this is our object, and this is our background. And this table also indicate the mean and confidence interval, as this is a mean and this is a confidence interval. So as you can see here, both of the CW attack came from different distributions, but for the FGSM and BGD, they almost came from the same distribution. And this is also observed in using ResNet 101. Section we compare adversarial perturbation energy concentration among previous attacks using L1 distance and entropy. So we, for each adversarial perturbation, we first calculate its energy distribution among 64 frequency components, where we calculated relative to all DCT coefficients in one image. So we calculated the entropy of the energy distribution and its L1 distance from one-shot probability distribution with a probability of 1 at the DC frequency, as shown here. Because the entropy by itself, it cannot say where is energy is concentrated, while the L1 distance while using the L1 distance and using the one shot probability as a DCT coefficient will help us where the energy is concentrated. So here we have two set of data samples, which is the entropy and the L1 distance samples. So to compare the perturbation energy concentration between any two attacks, we're gonna first test whether or not their entropy or L1 distance data samples follow the same distribution. So we're gonna have two hypotheses here, the null hypothesis and the alternative hypothesis. And the null will mean that both of the entropy for both attacks came from the same distribution or different distribution. So to compare all the previous attacks in pairwise, we run of course 6 different tests and one for each pair for either entropy or L1 distance, and we set the significant level to 0.05, and the above null hypothesis was rejected for all of them with a p-value close to 0, which mean all attacks have different perturbation energy concentration. So to see which attack method produced high concentration perturbation energy for the DCT component, we have done the same. We have applied the same technique for empirical bootstrapping with a resampling of 5,000 times, and the resulting estimated means and the confidence interval was a 95% is shown here. As you see here, the CW attack in both tables and figure for ResNet 18 and ResNet 101 both concentrated in the DCT coefficients, while the others is not. It's distributed among other components. In conclusion, using this statistical method in this paper, we have managed and based on chi-squared goodness of fit testing and bootstrapping, we can conclude the following: that the adversarial perturbation crafted by the FGSM, BGT, and CW attack can be modeled using the GGTCM, and the average DCT block energies of adversarial perturbation energy in the object and the background follow from different distribution for the BGT and CW, whereas they are follow from the same distribution for the FGSM. But for the CW attack, they put more, which is a very powerful attack, they put more energy in the background than the object of the image, while the FGSM and CW attack does not. For among the FGSM and the BGD and CW attacks, the perturbation energy distribution within a DCT block in case of the CW attack, it's highly concentrated in the DC coefficient, where these findings can help us in the future to protect DNNs and improve the AI security. That's all for today, and thank you.